What we're going to do here today, guys, is talk about lesson 36. Lesson 36 is really the first two parts, super easy, super stuff that you guys have done before. We're just bringing it to the next level here. And that is, we're just going to deal with angles that are greater than, or even less than, or outside of 0, 360. And what we're going to use here is the fact that we have something called coterminal angles. And I have talked about coterminal angles before. Coterminal angles are angles that differ by an integer multiples of 360. So 1 times 360, 2 times 360, and so forth. These are called coterminal angles. They are the same position on, let's say, unit circle. Hence, if I started at 30 degrees and I spun around 360 degrees, where do I stop? Still at 30. But if I went the initial 30 and went around some more 360 degrees, I actually went 390 degrees, right? And then at that point, I can keep going around another 360 and keep adding 360 to it. Now, if I was at 30-degree turn and I had you guys close your eyes and I spun around or acted like I spun around 700 times, you guys wouldn't know when you guys opened your eyes. Because you guys would open your eyes, I'm still standing at 30 degrees. Some of you guys would be like, oh, maybe you turned 5 times. Maybe you didn't turn at all. Maybe you turned to 700 times like you told us you did. They're all coterminal angles. And here's the cool thing, is that I also can go backwards 360 degrees. So if I turned negatively from 30 degrees, I would actually be at negative 330 degrees. It's the same thing as positive 30. So, to highlight this idea that we're going to have to not only find positive coterminal and negative coterminal angles at times, I want you to take these 3 angles here, and I want you guys to find one positive coterminal angle and one negative coterminal angle. So, if it's a positive angle, it's really easy to find a positive coterminal angle. Because all you have to do is what? If I'm already positive, to stay positive, I will add positive. So if I take 45 and I just add 360 to it, I end up where? What's 45 plus 360? It's 405. 405 degrees is a coterminal angle, and it's a positive coterminal angle. But if I'm at 45 degrees, what's the easiest way to get to a negative coterminal angle? Subtract it. Take my initial angle and just subtract 360. Where would I end up then? Don't all answer at once, guys.
Well,
Negative 315. There's a positive and a negative coterminal angle to 45 degrees. Both of those, if I turn 405 degrees or negative 315, I would end up at 45 degrees. That's a nice angle. We deal with those all the time as in 45s. What about 236? That's definitely not one of our reference angles. But does it change anything? No. What's the easiest way to get to a positive coterminal angle? Add 360. And if I do that, what do I get? 596. And if I wanted to find a negative coterminal angle, I will just take 236 and I end up with a negative 124. Pretty easy. But now on our third example, it's a negative 660 degrees. So to find a positive and a negative coterminal angle, what am I going to do? Every other time I added, right off the bat, I said, no matter what, I'm just going to add 360. So maybe let's try that. If I add 360, where am I at? It's a negative 300. What did I just find? I found a negative coterminal angle. Wait, Mr. Konchak, you added 360 and you found a negative coterminal angle? Yes. It's because the answer was negative. So now, if I wanted to find a positive coterminal angle, I'm just going to do what again? Add 360. I'm not going to subtract 360 from the original because that would also find another negative. If this would have been like a negative 1,000 degrees or so, I would have to add multiple 360s to get to the positive side, right? So just be careful that this is one of them. And then if I add 360 again, where am I? 60. There's my positive. Mr. Konchak, why is this even relevant? Why do I care? The thing is that what we're going to do today is go back into lesson, I think it's 24, 25, or 26. I'm not 24 or 25, I think it is. And we took trig functions and we added them together. We're going to do that today, but our angles are not necessarily going to be between 0 and 360. They're going to be negative angles. They're going to be angles that are larger or smaller than those. So we need to fix it. And wait, what is the connection? The connection is, if I asked you the cosine of negative 660, what is it equal to? You could take your calculator out. Bam, you got a half. But why? Why is it 1/2? It's because the cosine of negative 660 is the same thing as the cosine of negative 300. Why? And why is that equal to the cosine of 60? And if I was given a choice of those three, which one would you choose to take the cosine of?
60.
60. Because it's on our unit circle, and it's one of our reference angles, right? All three of them are the same because they're coterminal angles, which means they are actually in the exact same spot on the circle. Makes sense?
Yep.
I'm either turning 60 degrees, or I'm spinning backwards 300 degrees, or I'm here and I spin one complete revolution and spin another partial to get to 60 again. All of them are in the exact same spot. I'm getting dizzy. So, those are all the same. And that's what makes this so awesome, is because I can take something that looks complicated and make it easier for myself. So, let's put this into play. We also, to put into play, is the fact that we know that where I am on the unit circle, first, second, third, or fourth quadrant, our different sine, cosine, and tangents take on different values as in sine-wise, right? So we can also break everything down to its reference angles. And that's what I like to do. I don't necessarily like to leave it in terms of negative, or say even negative 300. We could go on the unit circle, find negative 300, and put its value down. But I like to say it's definitely cosine of 60, because that would also be its reference. So let's talk about that. The sums of trig functions. I've only got two little rules for this one. And the first one is switch all your angles to their coterminal angles between 0 and 360. Kind of what we were just trying to do here on the last slide. Switch it all to between 0 and 360. Doesn't always have to be. Technically, I could say from negative 360 to 60, because my next step would be to write their reference angles. And then you just evaluate them separately before you combine them with common denominators, not like terms. Common denominators. So we got 3 different examples of things that you got to combine. First couple are not too bad. We're going to use reference triangles for these ones. And then the last one, you're going to have to do a little bit of coterminal action to make it work. So, remember how to evaluate these. You draw them out so we can find the reference. 135 is somewhere about here, if I am guessing. So I draw my triangle. What's the reference? What's the leftovers to get me back? $45. So that means that cosine of 135 is equal to the cosine of 45. But wait, we're in the second quadrant. Cosine is cosine's what in the second quadrant? It's negative. So it's the negative of the cosine of 45. Remember, reference triangles always reference the first quadrant where everything is positive. So I will need to affix a negative where it's appropriate. Okay, tangent of 330. I think 330 is somewhere way down over here, right? Almost all the way. What's the leftovers? What's the reference? What's the reference? 30. But tangent in the fourth quadrant is negative. So it's not equal. Tangent of 330 is the same thing as the negative of tangent of 30. You can either add the negative or just subtract it, right? Now, you can get your unit circle out or draw your reference triangles. What's the cosine of 45? Square root of 2 over 2. Most of us, if we drew our triangles out, we would have 1 over the square root of 2. We fixed it by multiplying the top and bottom by square root of 2 over 2. Or square root of 2 over square root of 2. So we can cancel the square root of 2 on the bottom. Tangent of 30. So I'm just going to put a minus. It is square root of 3 over 3. If you did not draw your reference triangle out to figure that one out, why? Or unless you knew it. But again, I wouldn't see it as square root of 3 over 3. How would I see it? One over square root of 3, and then I'd multiply the top and bottom by square root of 3 to fix it. So it's square root of 3 over 3. We should be at the point, guys, that I shouldn't have to write out the reference triangles. You guys should automatically be doing that if you still need them. We need to start moving along at some point. Now we just got to put them together. You got to have a common denominator, and that common denominator will be so 3 and 3, 2 and 2. So a negative 3 square root 2 over 6 minus 2 square root 3 over 6. Because we're down in the second quadrant, cosine's negative. So the answer is negative square root of 2 over minus 2 square root 3 all over 6. And there's your answer. This particular problem, now we start to have this idea of negative 60. We can treat this in 2 different ways. You can find the coterminal angle, which we will do before we graph it, or you could just move down 60 degrees. Okay? So it's not too bad. Cosine of negative 60 is the same thing as cosine of what? What's the coterminal angle between 0 and 360? I'm waiting. Burning time on the video here. It's 300. Can't wait for Baikai to answer every question, guys. How did I get 300? I added 360. I'm not changing 210. I'm not changing 210 because that's between 0 and 360. Now at this step, I'm going to graph them to find their reference angles. 300 is here somewhere. Has a reference angle of 60. This one over here is 210. Has a reference angle of, how much further along from 180 am I? 30. We just have to worry about, are they positive or negative in those quadrants? Cosine in the fourth quadrant is what? Positive. So cosine of negative 60 is the same thing as cosine of 300, which is the same thing as cosine of 60. Cosine of 210. We're in third quadrant. Cosine is negative. And so cosine of 210 is the same thing as negative cosine of 30. And every single one of us should know the cosine of 60. It's nice. It's 1/2. And the cosine of 30. Square root of 3 over 2. And when you go to put those together, 1 minus square root of 3 all over, because it already has a common denominator. Isn't that grand?
Very grand. So grand.
Well, good. Not too bad. Try this one. I'm going to give you guys and pause the video. Find coterminal angles before you find your reference angles. Try it. So, on this particular problem, 570 is definitely larger than 360. So, to attempt to get it between 0 and 360, I will do what? I will subtract the 360. And it ends up being cosine of 210. So I'm okay with that. I'm happy with that. And what happens with the negative 765? I'm going to need to
add 360.
I'm going to have to add 360. And when I do that, I end up with a negative 405. That's still not there. So I'm going to add 360 again, which equals negative 45, which is still not there. Adding 360 again, you now end up at 315. So, cosine of 210 plus the cosine, or sine now, sine of 315, right? Is everybody okay with that? Now we can draw them. 210 is down here again. We just did that, had a reference angle of 30. 315, though, is way over here. Reference angle of 45. So now we can start to finish it. That means the cosine of 570 is the same thing as cosine of 210, which is also the same as the cosine of 30. I'm going to make that smaller. But it's not cosine of 30. It's in the third quadrant. Cosine is negative. So it's a negative cosine of 30. Is everybody seeing how I affix a negative to these things? Then, sine of negative 765 is the same thing as sine of negative 405, which is the sine of negative 45, which is the same as sine of 315. Or is equal to the sine of 45. But wait a minute, it's in the fourth quadrant, so it is negative. And so now, you evaluate. Take your unit circle, take out your reference triangles, draw them out. What's the cosine of 30? Square root of 3 over 2, so it's a negative square root of 3 over 2, minus the sine of 45. Square root of 2 over 2. So negative square root of 3 minus the square root of 2 all over 2 is your answer. If you don't believe me, just take your calculator out and get to a decimal for each one, and you find out they are the same. Unfortunately, calculators are approximations, so you need this. Now, what we have here now is called boat in the water problems or boat in the river problems. Doesn't necessarily have to be a boat. It could be an airplane in the sky, in the wind. It could be you riding a bike in the wind, because we know that the rate of the wind or water plays a big factor in your speed. If you are going with the wind or water, you go faster. If you are going against the wind, you go slower. Think back to your days of riding your bike. If you ride your bike on a windy day, would you rather go with the wind or against the wind? I think I'd rather go with the wind. Unfortunately, usually you have to turn around and go back. So, therefore, you're going to have to pedal harder or put more energy into going against the wind. Same thing for boats. Guys, if I am paddling a canoe on a still pond 5 miles an hour, I've got my canoe or kayak, I'm going 5 miles an hour, and I take that, and that's my ability, and I take that and put it into a river. And I like to go down the river, so the river is going 3 miles an hour. And I paddle my usual 5 miles an hour. How fast am I actually going to go?
Not very fast.
8 miles an hour, because I'll add my speed with the speed of the river. Now, I got to return back home and go back upriver. How fast am I making that trip now? 2. Because my 5 mile per hour speed will be counteracted with the 3 mile per hour current going down to give me a 2 going up. Okay? So, how does this all work? It all works off of distance equals rate times time. There are 2 different equations, and I should have probably switched these 2 around for here, is that these 2 are the rates, time equals the distance. And those are little D's on here, if you can't see. They look like O's. D's and U's, down and up, is what it stands for. Because each time you're going up or down the river, things are different. Your speeds, your times, possibly your distances going up or down are different. But they will be connected at the end. So, why, when I'm going with the water or with the wind, I got B plus W, where B is the boat's speed and W is the water's speed, or airplane and wind, so forth. I'm adding them together, because when I'm going down, I'm going with. When I'm going against, I got to subtract the wind's speed from my own or from that boat or plane. Make sense? I am, for our problems, always going to use B and W. Whether I'm talking about a boat, I'm talking about a bike, or a plane, or whatever. So I'm always going to stick with the same variables just to be consistent. They're going to give you some kind of connection. I can row 2 times as fast as the water. There's a connection there. I am going to make the same trip in twice as long as it took me to go downwind as I go upwind. Something on those lines. And so there's always a connection that's going to get us down to 2 variables, 2 unknowns, or 2 equations, 2 unknowns that we can solve for. So our first problem says one day Shelby found that her plane could fly 5 times the speed of the wind. Connection. She flew 396 miles downwind in a half hour more than it took her to fly 132 miles upwind. More connections. What was the speed of her plane in still air, and what is her speed of the wind? We say the speed of the plane in still air is because when you solve for B, you're finding how fast it goes if there was no wind gusts or no wind at all. Just like the water is just by itself. What's the wind or the water? So, let's just start listing some of the things we know. Speeds. Wait a minute. The boat in water, or the plane in water, or wind in this case, are they the exact same speed? No. She can do what? Her plane can fly 5 times the speed of the wind. So that means B is equal to 5W. Would you guys agree with that? Do we know distances? What's the distance down? What's the distance down or with the wind? 396. Do we know the distance up? 132. Well, if you think back to those 2 equations, and I'll write them down here, the only thing we don't have a connection right now is our times. Oh wait, we do have a connection. What was that connection between time down and time up? Was it the same? Did she say that she took the exact amount of same time for both? No. It says that there was a half an hour more downwind than it was upwind. So that means if I take upwind's time, I can do what to it to get downwinds? If I take upwinds and I add a half an hour to it, I'll get how long it took her to go downwind. She flew downwind for half an hour more than she went upwind. Sometimes it makes more sense if you take those distances out of there. Now, what were those equations? It was B plus W, and that would be for your time down, distance down. And I would subtract the wind if I'm going up. Start loading in the stuff you know. Do you know B or W? Technically, you have a connection. B is 5W. So 5W plus W times something equals, at this point I'm going to leave time out for now, because we know D's, the D's are pretty concrete. What are the D's? Time down, or distance down, I meant. 396. If I'm going against the wind, I got to subtract, right? B was 5W. So 5W minus W times something for time is equal to 132. What was that connection between their times? This top one here should be a TD. But TD is equal to TU plus 1/2. TU plus 1/2. And so, if that's the case, I'm going to leave TU as TU. How many variables do I have? I have a W and a TU. 2 variables. How many equations? 2. Now, I'm going to clean them up. What's 5W plus W? It's 6W times TU plus 1/2 equals a 396, right? And what's 5W minus W? 4W TU equals 132. What should I do with that 6W? I need to distribute. So I'll get a 6W TU plus 3W equals 396. Those 2 equations are what we're going to use. This is a unique problem type. I don't have just W equals because I have a W times a TU. I can't separate those guys. But what I can do to make this a lot easier is, can I isolate a WTU? Can I act like a WTU is its own thing? Yes. Take a look at right here. What if I divided both sides by 4? Would I just get a WTU? And where else do you see a WTU? Right there. And so, I am going to divide both sides by 4. And so, a WTU is equal to, what's 132 divided by 4? $33. And if that's the case, can I just substitute it into there? So it'd be 6 times 33 plus 3W is 396. Can I solve that for W? Yes, solve it for W to solve for TU. Your homework, ladies and gentlemen, is page 260, 6 through 8, 13, and 24. Have a great day.